Hi guys, I have received several requests from fellow engineers asking to discuss the procedures involved in the simplified method of raft slab design, which is outlined in AS 2870 clause 4.5, in particular the use of the graph in figure 4.1, which is under clause 4.5.2. This graph is used to work out the overall required depth of the slab. The graph is essentially an empirical fit to the deemed to comply slab design solutions, which is shown in section 3 of the standard. I believe this graph is located on page 44 of the Australian standards. The simplified method is located under section 4 of the standard, designed by engineering principles. This section primarily allows the designer to work outside of the scope and modify the deemed to comply designs contained in section 3. So the designer can go out and modify the rib spacings or beam spacings, but as long as it takes the same shape of slabs which are covered in the deemed to comply designs. The process involved in the simplified method is as follows. 1. Work out the minimum required slab depth using figure 4.1, which we will thoroughly cover in this video with a worked example. 2. Ensure that all design parameters are within the range of the table below, which is again outlined in clause 4.5.1. The table has a series of design parameters, as you can see in the first column, which needs to be carefully checked against the range shown in the second column of the table. So here, for example, we have in the first column we have the YS value, which is the characteristic surface movement. Then in the second column are the limiting values that we could use. Generally, you can obtain the YS value from the soil report or through a geotechnical engineer. And here we could clearly see that the limiting values for HS, the depth of suction, if HS is greater than 3, then you can use 10 millimeters to 70 millimeters. And for HS less or equal, I think the code should change that, but less or equal to 3, we can use 10 millimeters to 100 millimeters. And there are many other parameters, such as differential deflections, the slab span. There's also beam spacings, whether it is a rib for a waffle slab or stiffened beams for stiffened raft slabs. Minimum depth of any beam must be greater than 0.8 maximum beam depth. Unfortunately, this requirement came across as very confusing for some engineers. So let's talk about it here, and I've given an example. Let's take an example. Say we have a 385 deep waffle slab, and we want to provide a 500 millimeter deep and edge beam to satisfy the overall stiffness requirement of the slab. So the depth of any beam in this case would be 385, and the maximum beam depth would then be 500 millimeters, which is what we are proposing. Therefore, 0.8 of 500, which is 400, is greater than 385 millimeters, and therefore does not conform with the table range requirements. The simple way of looking at it is saying, okay, the maximum beam depth that we could have in this case would just be 385 multiplied by 1.2, and that'll give you about 462, rounded off to 460. This is just another way of saying that 385 is then greater than 0.8 multiplied by 460, which then conforms with the table range. In saying this, however, we then need to take away that value and recalculate the requirements of stiffness of the entire slab based on a 460 deep and edge beam, and check if it is satisfactory or not. In generally speaking, the slab as much as possible needs to be in a uniform and symmetrical shape to safely distribute the internal forces across the stiffening beams. Internal forces here refers to shear, moment, torsion, axial compression, and tension. This is why the simplified method does not allow a great variation between beam depths. It is also important to note that most of slabs which were previously tested to derive figure 4.1 were standard stiffened raft slabs with a reasonable uniform shape. And this was performed many years ago. A waffle slab, generally speaking, is probably able to redistribute moment and shears through plastic hinges a little better than a stiffened raft slab due to the numerous amount of joined ribs, as we are creating more nodal points between the ribs. But I guess this is a completely different discussion, which we will maybe leave for another time. With the rest of the table, we then have the beam width, which is between 110 to 400 millimeters, design distributed loads, which is less or equal to 10 kPa. And remember, this is to include the slab weight as well. You should include the slab weight. Design edge line load, which is less or equal to 25 kilonewton meters. That's including the slab weight. Then finally, we have the minimum slab mesh requirements for varying slab lengths. The third step in the process is slab strength shall be satisfied by ensuring ductility to conform with clause 4.4i, as shown below. Now, with this clause, we need to make sure that the ultimate moment capacity and hogging and sagging of the section capacity is greater than 1.2 times the cracking moment, where mu is the ultimate moment capacity of the section and hogging and sagging. So we need to do this separately to check for both mode of actions, where Z is the section modulus in hogging and sagging, and Z is I, which is the uncracked second moment of area, or second moment of inertia, divided by Y, which is the distance between the centroid of the section to the extreme fiber in tension, to the extreme face of the concrete that is in tension. And FCT is the concrete tensile strength, which is 1.8 MPa in hogging and 2.7 MPa in sagging. These values were derived based on the compressive strength of the concrete being approximately 20 MPa. Just before we go through the process of using figure 4.1 to determine the minimum required depths of the slab, there are a couple of things to note. One, the slab mesh requirement stated below is only minimum, and it is important to check areas of the slab where brittle floor coverings are used, such as floor tiles. So if you have more than 16 meter squares of brittle floor coverings, then you may need to refer to clause 5.3.7, which is shrinkage and cracking control, for more information. You might have to use a higher grade mesh like SL92, or provide additional control joints in the brittle surface. So I recommend you to go back to this clause and have a read of it. Number two, the second thing to note is that it is not necessary to use a design stronger than the standard design for the site classification, nor is it permitted to use a design weaker than the design given for the next lower site class. Now what that means is, let's say for example we have a H2 site with a YS of 70 millimeters and a differential deflection of 30 millimeters. And the slab depth determined from figure 4.1 happens to be 400 millimeters. Then it is not necessary to use a design stronger than the standard design. So we could still probably get away with using a 385 freeboard if we stick with the simplified method. Okay, finally, so let's get straight into an example. Step 1 in the process of this raft slab design is to work out the minimum required depth using figure 4.1. So let us take an example here. Say we have YS, the characteristic surface movement of 75 millimeters, which is a H2 classification, and you can obtain that from the soil report. And we're doing a single story home. The depth of suction is 2.3 meters, and we will take this home to be located in Epping, which is in the north. Epping is a suburb in Victoria, located in the north. We will talk a bit more about the depth of suction and how we derive that. The slab type is a waffle slab, about 19.69 meters by 11.29 meters. The wall construction material, we will take that as lightweight cladding. And the aim of this exercise is to determine the slab depth D, using figure 4.1. So the step 1, we need to count the number of beams or ribs running perpendicular to the short direction and perpendicular to the long direction. We have 17 beams, that's including the edge beams, okay? So we have 17 beams running perpendicular to the long direction and 10 beams perpendicular to the short direction. This is including, like I said, including all the beams, including the edge beams as well. Step 2 is determine the average width of all the beams in both directions separately. In the long direction, we have 2 edge beams, which are 300 millimeter wide each, and we have 15 internal beams or internal ribs, which are 110 millimeter wide. Therefore, the average beam width for the entire long direction would be 2 multiplied by 300 plus 15 multiplied by 110 divided by the total number of beams, which is 17, and that'll give you around 132.35 millimeters. Similarly, we do it in the other direction, in the short direction. We have 2 edge beams, which are 300 millimeter wide, and we have 8 internal beams in between the edge beams, which are 110 wide. Therefore, the average beam width for the entire short direction would be 2 times 300 plus 8 multiplied by 110 divided by 10, and that'll give you 148 millimeters. Step 3. Confirm the value of the depth of suction for the chosen site. And in this case, we have Epping, which is a suburb in Melbourne, located in the north of the CBD. In figure 4.1, there are 2 linear lines, as you can see here. One line represents the normal soil profile, where the depth of suction, HS, is less than 3 meters. The other line represents the deep-seated movement profile, where HS in this case is greater or equal to 3 meters. So how do we know what depth of suction to use in Epping in this case? Well, we need to look at we need to look up the Melbourne climate zone maps in figure D1 in the standard. I've marked it here, an approximate location in red, where Epping may be, and it is basically located north of Melbourne CBDs. And it is, as you can see here, it is climate zone 3. Then what we do is go to table 2.5 and read out the corresponding depth of suction for that site, which in this case HS is 2.3. So for this example, we need to use the first line on the graph to determine the slab depth, because 2.3 is less than 3. Step 4, determine the differential deflection delta from the construction materials given to us in the problem for both directions. We do that separately as well. Then we need to determine the movement ratio, which is YS divided by delta. And that movement ratio is the value on the y-axis of the graph on figure 4.1. We were given a waffle slab to support support lightweight cladding frame. We then go to table 4.1 and look up the corresponding differential deflection values. We need to do this for both directions. Many times though, engineers tend to forget to check it for both directions. It is important to assess the stiffness requirements of the slab in either direction, well, in both directions, and then adopt the worst case slab depth requirement to cater for that differential deflection, or to cater for the worst case differential deflection. So in this case, we need to select the lesser of the two values in the column of tables 4.1. Longer direction, we can start off with that. The length of the beams perpendicular to the longer direction is 11.29 meters, which is basically 11,290 millimeters. Okay, we need to take the total length from one end to the other. So if we do have a slab with a rebate, we can take the total length between the rebates, but then ignore that section of the rebate in our calculation. But it has to be the total length of the entire slab. So L in this case is 11,290 divided by 300, which gives you 37.63 millimeters, or 40 millimeters. So lesser of 37.63 or 40 millimeters. Therefore, delta in the longer direction, we can choose 37.63 millimeters. YS over delta will be 75 divided by 37.63, and that will give you 1.99. Now 1.99 is the value to select on the y-axis of the graph. Now we can do the short direction, same thing. Length of the beams perpendicular to the short direction is 19.69, which is 19,690 millimeters. L over 300, 19,690 divided by 300 will give you 65.3 or 40 millimeters. Then we take the lesser, in this case will be 40 millimeters. The delta in the short direction is 40 millimeters. The movement ratio, YS over delta, will end up being 75 over 40, and that would be 1.875. Again, that's the value on the y-axis that we select. Step number 5. Determine the required slab depth from figure 4.1 in the long direction. Now for beams perpendicular to the long directions, we have the following worked out parameters. This is just a zoomed image of the graph so you can see it clearly. Now we all agree that HS is 2.3, which we will use the first line. Number of beams is 17 in total. Beam length 11,290 millimeters. The width of the slab is 19.69, so the width of the slab is perpendicular to the beam length, and the movement ratio is 1.99. If you remember, the B average, or the average width of the ribs is throughout the entire slab is 132.35. For the value of 1.99 on the y-axis, if you go down, so you actually go right straight to the linear line, then go down, you'll get 8.65 approximately on the x-axis. Therefore, what we say is 8.65 is equal to log BW, or B, which is average width, times D cubed divided by 12 divided by the total width of the slab. Upon substitution, 8.65 is equal to log 17 multiplied by 132.35 D cubed divided by 12 divided by 19.69. We've got to remember though, the units of the beam web is in millimeters, and the units of the entire width of the slab must be in meters. Sometimes we make a mistake there and we get wrong values. So, okay, upon substitution, this is log to the base 10. So it's not ln, it's log. Whenever you see log without any number at the bottom, that's automatically log to the base 10. So how do I pick this equation apart? I say 10 to the power 8.65 is equal to the right hand side, which is in this case 9.52 to D cubed. Okay? And therefore D will be about 360 millimeters. With these, a minimum depth of beams perpendicular to the long direction. Step 6, we're almost there. Determine the required slab depth in the short direction. So for beams perpendicular to the short direction, we have the following worked out parameters. HS is 2.3, number of beams in this case is 10, the beam ribs length is 19690 millimeters, the width, remember it's in meters, so that's 11.29 meters, the movement ratio 1.875, and the average width of the ribs is 148 millimeters. For the value of 1.87 on the y-axis, we have approximately 8.6 on the x-axis. Like before, 8.6 is equal to log BD cubed over 12 over W. And then we say 10 to the power 8.6 is equal to the right hand side after working everything out, which is 9.522 D cubed. Therefore, D in this case would be 331 millimeters. Now, this minimum depth is is for beams perpendicular to the short direction. Step 7 is to selection of the appropriate slab depth for the design. In general, we will look at the depth that we worked out, 331 and 360, and then say, okay, we will do the worst case scenario and choose 360. So from previous calculation, we determined that, we have D perpendicular 360 in the long direction, and slab depth required for beams perpendicular in the short direction is 331. But you got to remember that this is a single-story home supported on a supporting a clad frame, and the site classification is H2. The minimum slab depth, as per section 3, the deemed to satisfy from figure 3.4 is 310 millimeters. So therefore, it is not necessary to use a design stronger than the standard design for the site classification. So we may, in this case, adopt 310 millimeter slab depth to conform with section 3, figure 3.4. So because it was, I think we're lucky in this case, because it was supporting a clad frame, we would have, you can use 310. If it was an articulated masonry veneer, then the minimum depth here would be 385. So we couldn't have used 360. We would have had to use a 385 millimeter slab depth. But I think we were lucky in this case that the deemed to satisfy section has saved us and probably saved the client some money as well. Okay, so far, like we covered in this video, we mainly covered the first steps in the process of the raft design using the simplified method. I hope you enjoyed it. In the future videos, we will cover the other two steps, which is pretty tedious. The other two steps is to ensure all design parameters are within the range outlined in the table under clause 4.5.2. And the third step is to check the slab strength by satisfaction of ductility to conform with clause 4.4i. Other common questions we could cover in later presentations. These questions from fellow engineers whom I've worked with along the years, and some of these questions I'll share with you. We can cover that later on. Can I use the simplified design method for the following situations? 1. P-class sites. Second question, sites with existing trees and or removal of trees. That's interesting. 3. Sites with removal of structures. 4. Sites with level 1 compaction. Can I use graph 4.1 if I have that situation? 5. Sites with partially or fully suspended slabs. Now I've seen engineers use it all the time with this situation. Is it acceptable or not? Number 6. Sites which has a YS value more than 100 millimeters, but the slab is fully suspended with piers or piles, and the pier depth is well below the cracking zone. Where does it lead us here? Am I allowed to use it? Can I reduce the YS value to consider for a deeper pier depth? Interesting. 7. Can I design a total different slab system such as a flat plate without stiffening beams or ribs? Previously we spoke about redistribution of moments and how having ribs helps with redistribution of moments. Can engineers design a flat plate using this system? Is it the same, provided that the stiffness is the same? Well, this is probably this can we can talk about this for a very long time, so we will save this for another video. Now the last question, the other question that many engineers, including myself, I have, is what happens to soil suction HS and thus soil movements with climate change? And then it makes us think, okay, how long is figure 4.1 valid for? As we're aware that the TMI values, especially for Melbourne and Adelaide, is decreasing by time. There are clear evidence of increase in seasonal temperature and general rainfall decline. The CSIRO in 2007 has made some predictions of climate change for Australia. For example, in southeastern and southwestern Australia, they're expecting that in 2030 and 2070 the temperature will increase by about 1 degree and 3 degrees respectively. And not only that, but the winter and spring rainfall is predicted to decrease significantly. So based on this prediction, Peter Mitchell in many research papers expected a drop of about 30% in the TMI for Melbourne between 2012 and 2030. And for Adelaide, he was expecting a drop of 40% in TMI. So where does this put engineers in terms of design liabilities in the future? This graph in figure 4.1, we have to remember that it was developed at a particular time in the 60s and 70s where climate change was a lot different than today. So the question here probably refers back to the Code Committee to give us some sort of indication of where these predictions are at and whether this would affect the site classification. A great drop in the TMI means that the predicted movement, which is YS value, would dramatically increase. Peter Mitchell gave some predictions of an increase in the YS value by time. So for Melbourne, for example, he said that a YS value of 35 millimeters in 2012 would end up being 45 millimeters by 2030 and 60 millimeters by 2070. So here are some interesting questions you may want to think about till we meet again next time. Thank you all for listening, and I hope this has helped.